Okay, so let us start. I welcome you to week 10 live session of distance system design. I'm Om, and today we will be doing some of the questions which are mainly focused on the reduction of state table and arithmetic circuits using the sequential design. So let us start. The first question is, which of the following statements are true? 1. Two states are equivalent if they move to same or equivalent state for same input and generate same output. Second is, two states are equivalent if they move to same or equivalent state for same input and generate different output. States A and B are equivalent if then B is also equivalent to A. For two states to be equivalent, it is sufficient to check if next state is same or equivalent for the same input. Right. So only 1 and 3 are correct. So for states to be equivalent for, let's say, states A and B, for them to be equivalent, their next states, this should be equivalent to this, and this should be equivalent to this also, as well as output. This should be equivalent to this. That is why this is not correct. Here it says different output, and this is not sufficient. We have to check output also. So only 1 and 3 are correct. So this option. Okay, so next question is, consider the following state table, and we have to tell which of the following are not equivalent states.
Can you show all options, sir?
Is it visible?
Yes, sir, visible.
So let us see one by one. First, let's see G and C. C input is DA, G input is DA, output is also same. So these two are equivalent. Then it is I and D. I is EC00 and D is EG00. So this G has now become C. So I and D are also equivalent. Let's call it maybe D for now. F and B. B is CD10 and B is and F is GI10. So output is same. G equal to C we have established. So this is C, this is fine. And I equal to D we have also seen that is also true. So this is T and D. So these two are also same. And B, B. Last one is H and I. So this by elimination we can see like H and I is the one, but anyway we can let's try to see it otherwise also. Here it was E and C, D and G. G equal to C is true, but D equal to E, that is not true. See, D in its output has 0 0, E in its output has 1 0, so D can never be equal to C. Sorry, D can never be equal to E. Since both can be same, so H cannot be equal to I. So answer is H and I are not equivalent. Is it okay?
Yes, sir.
Okay. So the procedure is simple. We just have to check states one by one and keep on reducing those which are the same. Okay. So next question is the minimum number of states in the above questions are. So we have to determine the minimum number of states here. So we have also to check. So currently the states that we have are A, B, C, D, E, H, and J. Okay, so let us try maybe, yeah. So you can see this one and this one are also same. So we can remove this. This is E. So J is gone. Now H maybe let us see. Is H equal to D and C? You can check maybe H and A. Is D equal to A? Okay, this is not possible. Okay, so I think these are the reduced states. We have six minimum states. We exhausted all the possibilities because for any state to be equivalent to H, this D must be equal to something. And in D we have E. And this E is actually has output 1 and 0. And only other state which has output 1 and 0 is this one, this one. Okay, so you can check all the states. So minimum states is 6. Okay, so it is not that difficult. You can also go for the triangle method, which will definitely give you some answer. So I'm not wasting time on that here right now. But to confirm, you can check that. Okay. So is there any doubt? Can we move on?
Yes, sir.
What is the maximum number of flip-flops required to implement a state machine with 6 states? So this is kind of a trick question. So it is asking what is the maximum number of flip-flops. So
6.
yeah. So the minimum number is actually if there are like in
Log
yeah,
2 base.
log 2 number of states. This is minimum flip-flops. But maximum you can have each flip-flop storing one state. So similarly, the next question is the same. Minimum number of flip-flops required to synthesize sequence circuit with n states. So here now it is asking minimum. So this will be log 2n. Right? So basically each flip-flop can have two states, say 0 and 1. So okay. See the next one. Please stop me anytime if there is any doubt. Okay. Consider a Moore machine with 4 flip-flops, 2 inputs and 6 outputs. Determine the missing number of transition arrows leaving from the number of leaving and the number of transition arrows entering the state. Okay. So let's take an example of a state diagram first. So whenever we draw a state diagram, let's say just between 3 states, S0, S1, S2. So we have, let's say, input is 0, output is something. So it is a Moore machine, right? So is Moore machine independent of uh, output or dependent on? Is the output dependent on next state on input or not?
Yes.
So in more machine, output is independent of input. We saw in last lecture. Right? So output will be fixed. Let's say 0, 1, 2 associated with string. Okay. Anyways, my point was you will have 0 or 1 transitions. Correct. Considering you have only input one input, which is x, which can be 0 or 1. Right? So maybe I want to take this then 0, 0, 0. Anyways, something like this. Now if we look, we had here only one input. The transition arrows leaving and the transition arrow entering a state. The transition arrows entering a state here is 2 and leaving a state is also 2. So we can maybe lay out some formulations. So let us say take a simpler example. Uh, let's say now the number of inputs is 2, x0, x1. It can have 4 values 0, 0, 0, 1, 1, 0, 1, 1. Right? Now what will happen on each of these states? 1, 1, 0, 1, 1. Now the arrows leaving are equivalent to number of inputs, right? So this arrow maybe can come back, this arrow maybe can, or this arrow can go here, this arrow can also go here, this arrow can come back. Like anything is possible, but that is for sure number of arrows leaving equals to number of inputs. Is it clear?
Yes, sir.
Okay. Now the second thing is number of arrows entering a state. So maybe to understand this, we can take another example. So again, let me take three states and again two of inputs x0, x1. Let's say all the inputs come to this state only 0, 0, 0, 1, 1, 0, 1, 1. From here also 0, 0, 0, 1, 1, 0, 1, 1. From here also 0, 0, 0, 1, 1, 0, 1, 1. Right, we are taking an extreme case, so this is a possibility. Right, like whatever input you get, you always end up at state as 0 from wherever you start. Right, so though basically the number of arrows entering in S0 are total 3 states into 4 inputs. Right, so basically the number of arrows entering are number of arrows entering a state equal to number of states into number of inputs. And the question says, if four flip-flops. So if we have four flip-flops, number of states can be number of states, maximum number of states, 2 to the power 4, that is 16. So the number of states can be 16. Number of inputs is what? Uh, 4. Okay, number of input conditions. Right, because number of inputs are 2, but input conditions are 4, which is same as number of input conditions. Right, inputs we have only 2, x 0 and x1, but the number of input conditions are 4. This was 4, this is 16 into 4, 16 4 was 64. So answer is 4 and 64. Right, for 2 inputs, 4 arrows given, 4 flip-flops we have, so that is 2 to power 4 into 4, which is 64. Is it clear?
Yes, sir.
Okay. So we have this state table. We have to reduce it using the triangular method and then fill out whatever these values are. P, Q, S, T, and R. So try making a triangle, then let us solve it together. So let us draw a triangle. So let me take a screenshot of this. So let us have this on the side for our reference. Okay, let us select neighbor table. So this is the table. Now first is A. So is A equal to any of these? The CA. So A has output 1 and 0. And all these have output 0 and 0. So A cannot be equal to B, C, D, E, and G. So we can directly put cross. For A equal to F, we have A equal to B and E equal to F. So again, A equal to B, A cannot be equal to B. We have just seen. This is also not possible. So A cannot be equal to F. Last remaining is A equal to H. For A equal to H, again A equal to H, the same thing, equal to G. Equal to G is the condition. Please, Nishan, please let me know if you are not falling at any place.
Okay, sir.
So next, let us look for B. Is B equal to C, D, E, F, G, and H? Let us see the output first. So B can be equal to these, cannot be equal to these. Right? So we can totally remove F and H. F and H. And is B equal to C? For B equals to C, the condition is again B equal to C and F equal to H. So let us write it for B equal to C F equal to, which is the condition, of B equal to D, C and D should be equal. If and are equal, means C and D is the condition. For D equal to E, B, C and D should be same, and A and F should be same. Now we have seen A cannot be F right here, so this is not possible. Now for B and G, we have C equal to D and F equal to H. So let us write that F equal to H. Okay, now for C can have these possible combinations. E is again 0 0 output, so F and H cancel out. F and H are cancelled. For C equal to D, we have B equal to E and H equal to F. B equal to E, H equal to F. For C equal to E, we have B and D, H and O. Then we have C and G. Of this B equal to D and H equal to H. H equal to H is fine. B equal to D equals. Now for D, so these two are not possible. For D equal to E, D equal to E and F equal to A. So H equal to A. For D equal to G, equal to D, F equal to H. For E, only G is the possibility. These two are not possible. And in G, D is D, A is H. H. For F, G is not possible. For F equal to H, we have B equal to H and F equal to G. So B equal to H is not possible because B has output this and H has output 1 and 0. So this is not possible. So now this F is not equal to H. This also cancelled out this one, and this one. For G, there is no possibility. So G and H are different. Okay, so let me erase these. Make it more clear. Okay, okay, this is also H equal to F. This is also Y. Okay, let me delete this. Just remove this. So the remaining ones are CE, this one, this one, this. We have one more F and A. So let us check F and A. F is not equal to right. A is not possible. So this is also actually closed. Okay. So now let us look at the possibilities. A
So
equal
can you
to
repeat once again, sir?
repeat what?
That yellow color marked ones.
So okay, so yellow marked ones are the ones like which have not cancelled in uh, they have not cancelled previously. So basically what we did was okay, let me remove this yellow thing. So till here was it clear? Till here.
Yes, sir.
So this is also not possible for G and H output is not the same. So anyways, so another thing is we have this F is not equal to H we have found out here, right? But we had considered, let's say, C can be equal to B if H was equal to H. But since now we know F cannot be equal to H, so we can remove these. Wherever we have F and H condition, we can remove those blocks also. So that is why I have like
Okay,
just
sir.
removed these. Also, I missed to remove this one earlier. F is A, where F equal to A, but we already have seen F cannot be equal to A in the first row or in the first column itself. So this one will also to be removed. This is also sorry, H equal to F. So now the remaining ones that we have are C, E, G, this, and this. Now we have to look if any of them are valid or invalid or what are the conditions. Okay. So now let us look at this. A will be equal to H if E equals to G. Okay, let us see is E equals to G. E will be equal to G if A equals to H. Let's also these two are like complementary. A will be equal to H if G equals to E and G will be equal to E if A equals to H. This we can gather from this block and this block. Right? They both say this thing. So these we can mark as equal. So let me write it. A equals to H and G equals to E. Till now. So now let us look at this C and E block. Okay, so B will be equal to D if C equals to E. Now let us look at C and D. C and E is this. C will be equals to E if B equals to D and h equals to a. So h equals to a we have already established. This is correct. So what this leaves us with is uh, this block and this block. What these two blocks tell us: B will be equal to D if C equals to E, and if we look at C and E block, C will be equal to E if B equals to D, which is the same thing again. C equals to E if B equals to D. So again we can write this is also as also true. B equals to D and C equals to E. This also gives us one more thing, like if you see these two, G equals to E, C equals to E, correct? Which is also true. We can see from here. We have just proven B equals to D. And C will be equal to G if B was equal to D, which is true. C equals to G equals to E. Okay, so now we can like, remove the redundant items from this table. So H is same as A, G is same as C, E is also same as C, this is same as B, correct? So the only remaining total variables are A, B, C, and F. Just all are uh, same. So this what this leaves us with, we have A, B, C, and this P should have been F. This should be F. And if we look at F's table, it is B, F, 1, 0. We can write here B, F, 1, and 0. And in this C table, B and R, what is R? In the C table, B, H, 0, and 0. And this H equals to A. So we can write it as A. Okay, so basically the whole question was to find these underlying variables P, Q, P, S, T, and R. So all these we have found out just by doing this reduction. Is this whole process clear to you?
Yes, sir.
Okay. So another question is, what is the most appropriate value of P? We have found out P equal to F. What is the most appropriate value of Q? So Q is B. Is B. Most appropriate value of R. R is A. Most appropriate value of S and T. S and T are 1 and 0. Okay. So these were all the four related questions. Okay. So if you see, like, this was a pretty lengthy question, but again it can have like four or five different subparts. So it is worth solving it. It is very easy. It is just we have to compare the variables and solve it by logic. So do practice more of these if you get the examples. So let us see the next one then. In the following state transition diagram, which of the following pair of states are equivalent? For this, what you should do first is make the state table. So if you can make the state table, either you can directly see if inputs and outputs are the same. So if the next states and the outputs are same for all inputs, then the then we can write. And if it is not apparent, we will have to make maybe the triangular table. Try it once. Okay, so let us see this. So, yeah. So let us make the state table. So then state x equals to 0 and x equals to 1 output. And this is a mode machine, so output is fixed. A it will be 0, B it will be 1, sorry, B it will be 0, C it will be 1 and D it will be 0. Now if x equals to 0,
A,
you're at, yeah, you come back at A. X
A,
equals
B,
to B.
A, C,
A, C,
A, D,
A and D,
A, C.
A and C. So just by looking you can tell, right? This and this are same. So they are same next states AC and HC and same set of outputs. So B equals to D. Is any other equivalent? Let us try to check that. Is A equal to B? For that B must be equal to C. And if we see B and C cannot be same because it's a 0 and 1. So A cannot be equal to B. What is it right here? A cannot be equal to C, they have different output. Is A equal to D? This is A and A. This is again B and C. And B cannot be equal to C because of this difference of output. A cannot be equal to B. B is also not equal to C because output are different. B and D we have checked. C cannot be equal to D because they have different outputs. We have checked all the cases. Only B and D are same. So that will be this answer. Is this true?
Yes, sir.
Last question is a 32-bit adder is used to add 64-bit numbers with multi-cycle approach. Calculate the total time required to add 10 unique 64 bits numbers if the delay of 32-bit adder is 20 milliseconds. Also note setup, hold, and propagation time of register is 2 milliseconds. So basically you have a 32-bit full adder. Um, we're trying to add some numbers A and B. Take out some sum and carry, which is with some flip-floppers, something like this. So with 32-bit and we have to do a 64-bit addition. So we'll have to do the use this adder 2 times, right? So for 164-bit addition, the total time is 20 milliseconds, which is 2 into 20 milliseconds plus 2 into this setup hold plus propagation times 2 into 2 plus 2. So this is total 40 plus 8, 48 milliseconds. Now we have to do 10 such unique additions. So the total time will be for 10 additions 48 into 10, which is 480. Okay, so one thing to note here is like again this question is worded pretty complexly. Like it says setup time, hold time, propagation time is 2 milliseconds each. So now what can that mean is that setup time is 2 milliseconds, hold time is 2 milliseconds, propagation time is 2 milliseconds. And if you add all that, it comes out to be near 520 or something. I'm not sure. It's 40 plus 12. Yeah, 520, but there is no such option. So what I think they mean is setup and hold time together is 2 milliseconds and the propagation time is 2 milliseconds, which comes out to be 480. So again, not a very well worded question, but basically the formula you should remember, and it was given in one of the videos also. So Total time is 2 into full adder time plus setup or hold, whatever are the additional times you just add them, plus propagation delay of register. That will be 2 times. So you just have to add everything and multiply by 2. Is it clear?
Yes, sir.
Okay, so these are all the questions I had for today. We have solved them pretty quickly today. So if you have any doubts, we can take them, else we can close the session. Jivan, you have joined late today. You have finished already. Where were you?
सर थोड़ा बाहर में था सर.
Okay. So anyways, so questions today were very easy. You can,
Oh,
sorry. Okay. So
okay
questions
sir.
today were easy. You can just follow from the recording. I will upload it right after the class. And if you have any doubt, you can email me.
Sure sir.
Okay, so uh, if there's nothing else, let us close early today. I'll see you in the next class. And most probably I will prepone or postpone my next class because I'm not available on next Monday. So either I will take it on Saturday or on Tuesday. So I'll discuss with the team and they will let you know. In any case, if there is any discrepancy, I will let you guys know. I have both of your emails anyways and nobody else practically joins.
Okay sir.
Okay then. Thank you guys.
Yes, thank you sir.
Thank you, sir.